When you think about Go, what's one of the first things that comes to mind? For a lot of us, it's concurrency. The ability to launch thousands, even millions of tasks with just that simple Go keyword. But have you ever really stopped to think about how that's even possible? Well, the secret isn't just the keyword itself, it's this incredibly elegant and efficient memory model working behind the scenes. And today, we're going to pull back that curtain and look at two of the most critical parts, the stack and the heap. I'm telling you, truly getting how these two work together is what separates writing Go code that just works from writing Go code that absolutely flies. So let's dive in.
So here's our game plan. First, we'll start with the basics, the difference between your program on disk and what it becomes in memory. Then, we'll watch how the Go runtime creates this memory world from scratch. The main event, though, is going to be a really deep dive into the dynamic Go routine stack. This is the real engine behind Go's concurrency. After that, we'll put the stack and the heap side by side for a clear showdown. And finally, we'll bring it all home by looking at how all this theory applies to the actual code you write day to day.
Okay, so first things first. Before we can even talk about the stack or the heap, we have to get one thing straight. Your program basically lives a double life. You've got the version on your disk, that executable file you make with Go build. It's just a static, predictable file. But then there's the version that exists in your computer's RAM when you run it. That's a living, breathing process. These are two totally different worlds, and that jump from disk to RAM is where everything interesting begins.
This slide really nails that separation. Over on the left, you've got your executable file. Think of it like a blueprint for a house. It has all the instructions, the machine code in the text section, and any materials that are already defined, like global variables in the data section. But look really closely at what's missing. There's no stack, there's no heap. Those concepts don't even exist at this point. They are purely runtime things. It's only when you actually run the program that the Go runtime wakes up, reads that blueprint, and starts building out the dynamic world you see on the right, inside your RAM. The executable is just the script. The stack and heap are the actual stage, built completely fresh for every single performance.
So how does that stage get built? What are the very first things that happen in those first few nanoseconds after you hit run, even before a single line of your main function is executed? Well, it's not random. The Go runtime follows a very precise two-step ritual to bring your program's memory to life.
And the order here is absolutely critical. Step 1, the heap is created. The runtime goes to the operating system and says, hey, can you reserve a massive chunk of virtual address space for me? On a 64-bit system, this can be terabytes. Now this is a key point. It's not actually using physical RAM yet. It's just reserving a giant playground for all future dynamic allocations. This is a clever trick to prevent memory fragmentation down the line. Once that huge space for the heap is reserved, only then does step 2 happen. The runtime creates the very first stack. And it's a tiny one, just 2 kilobytes, and it's built specifically for the main Go routine, the one that's about to run your main function.
Okay, everybody listen up. If you remember only one single thing from this entire explainer, please let it be this. Burn this into your brain. It's a super common misconception, even with experienced Go developers, that the runtime just carves out little pieces of the heap to use as stacks. That is 100% fundamentally wrong. The runtime makes two completely separate kinds of memory requests to the OS. It makes one giant request for the heap, and then it makes lots of small, individual requests for each and every Go routine stack. On Linux, for example, these are separate mmap system calls. The stack and the heap are neighbors, but they live in different houses, they follow different rules, and their memory is never, ever mixed.
And now we get to the real magic of Go. This is the feature that makes Go feel like, well, Go. The Go routine stack isn't just a tiny version of a normal thread stack you'd find in another language. No, it's a completely different kind of beast. Its dynamic, flexible nature is the single biggest reason you can fire up tens of thousands of concurrent Go routines and your system doesn't even flinch.
Just let that number sink in for a second. 2 kilobytes. That's 2,048 bytes. That is less memory than a short email. This tiny footprint is the entire starting point for every single concurrent task you launch with the Go keyword. It's an unbelievably small and efficient start, and it's the first major clue to understanding Go's whole concurrency model.
And this bar chart, wow, it shows you exactly why that 2 KB starting size is such a brilliant move. A standard OS thread, like you'd see in C++ or Java, usually reserves a stack of 2, 4, or even 8 megabytes right from the start. Let's just use 8 megabytes. That is over 4,000 times larger than a Go routine starting stack.
I mean, do the math. If Go used those traditional thread stacks, launching just 10,000 tasks would reserve 80 gigabytes of virtual memory before your program did anything useful. It would be totally impractical. By starting ridiculously small, Go makes massive concurrency possible. The runtime is betting that most of your Go routines are simple and won't need much more than that initial 2 KB. And it's a bet that pays off big time.
Okay, so that's the obvious next question, right? If a Go routine does something complex, like calling a bunch of nested functions, that 2 KB is not going to cut it. So how does Go handle this without everything just crashing? The answer is this really elegant automatic growth mechanism that's managed entirely by the runtime.
The whole process is this beautiful collaboration between the compiler and the runtime. It all starts with the compiler. When it's compiling your code, it sneakily inserts a tiny invisible check at the very beginning of every single one of your functions. It's often called a function prologue, and this check is simple. It knows how much stack space your function is going to need, and it checks if there's enough room left. If there is, great, your function runs like normal. But if the check fails, if you're about to run out of stack space, it doesn't run your code. Instead, it calls a special function in the Go runtime, which kicks off the whole stack growth process. It's kind of like a bouncer at a club, checking if there's room inside before letting you in.
So when that stack check fails, the runtime takes over and performs this incredible multi-step dance, all completely hidden from you. First, step 1, it allocates a new, larger stack, usually double the size of the old one. Step 2, it copies everything from the old stack over to the new, bigger one. Now step 3 is the really magical part, updating pointers. See, the old stack might have had pointers that were pointing to other variables on that same stack. After the copy, those pointers are now broken. They're pointing back to the old memory we're about to delete. So the runtime has to fix them. It scans through the new stack, and using some special metadata from the compiler, it finds every single one of those pointers and carefully adjusts it to point to the correct new address. Once that's done, step 4, it switches the Go routine over to use the new stack. And finally, step 5, it frees the old stack memory. Only after all of that is finished does your function finally get to run, completely unaware of the major surgery that just happened underneath.
Now, you might be thinking, if stacks can grow, can they also shrink? And the answer is, kinda, but with a big asterisk. Stack shrinking is an optimization, not a fundamental feature like growth. Let's say a Go routine grows its stack to 1 megabyte for a big task, but then finishes and is only using 2 KB again. That's a lot of wasted memory. So during a garbage collection cycle, the runtime might notice this and say, hey, this stack is mostly empty. If usage is low enough, it might perform the reverse operation, allocate a smaller stack and copy the data back over. But it's opportunistic. It only happens during GC, and it's not guaranteed. So think of shrinking as a nice bonus, not something you should rely on in your code. By the way, if you're enjoying these kinds of deep dives into Go's internals, you should definitely subscribe to our Gokun channel. We cover advanced topics like architecture and execution flow that you rarely see on YouTube, and it's all available for free. The link to the notes is in the description. Go ahead and subscribe so you don't miss out on our upcoming lessons.
Okay, now that we've gone deep into how the stack works, let's pull back and put it head-to-head with the heap. This comparison is really going to help crystallize the core differences and lock in that mental model. This table is the perfect cheat sheet. Let's just walk through it real quick. First, scope. This is the big one. A stack is fiercely private. It belongs to exactly one Go routine and one Go routine only. The heap, on the other hand, is like a public park. It's a single, shared space for all Go routines. Then there's lifetime. Stack data is simple. It's created when a function starts, it's gone when the function returns. It's totally automatic. Heap data is way more complicated. It lives as long as any Go routine is using it, and it's up to the garbage collector to figure out when it's no longer needed. Management. Because of that simple lifetime, stacks are lightning fast. It's just moving a pointer up and down. The heap is much slower. It needs a complex allocator to find free spots, and it needs the garbage collector to clean up old junk. And finally, source. As we've hammered home, they both come from the operating system, but they are totally separate, independent requests.
All right, enough theory. Let's connect all of this to the Go code you actually write. How do things like function calls and the Go keyword actually translate into these memory structures we've been talking about?
When you write a totally normal function call, say main calls a function A, you're not creating any new stacks. Both of those functions execute on the very same goroutines stack. Every time a function is called, a new frame gets added to the top of the stack, which makes the stack grow deeper. And when the function returns, its frame is just popped off the top, making the stack shallower. It's a simple, super efficient process, all happening on that one private stack.
But the Go keyword, now that changes everything. It's the magic wand. When you just call B, you stay on the same stack. But when you type go B, you're sending a special instruction to the runtime. You're telling it, I want you to create a whole new independent path of execution. And the runtime responds by creating a new goroutine. And as part of that process, it asks the OS for a brand new private 2 kilobyte stack just for this new goroutine to run on. This is the only way a new stack is ever created in a Go program.
And this slide gives you the perfect mental picture of what's happening. After main calls A and also launches go B, you have two parallel worlds. You have stack 1, which belongs to the main goroutine, and it has the frames for main and A. And you have stack 2, which belongs to the new goroutine, and it only has the frame for B. These two stacks are totally isolated from each other. But notice that shared cloud at the bottom, the heap. They both have access to that single shared space. And that is the bridge between them. It's how goroutines communicate and share data, by passing around pointers to things that live in that common area.
So this brings us to the final piece of the puzzle. How does Go actually decide where to put a variable? Should it go on the stack or on the heap? Well, the answer is a compile time process called escape analysis. The compiler literally analyzes your code to see if a variable's life is contained entirely within the function where it was created. If it is, perfect. It can live on the fast, cheap stack. But if that variable needs to live on after the function returns, or if it's shared with another goroutine, we say that it escapes. And in that case, the compiler makes sure it gets allocated on the heap instead.
Here's the classic example you'll see everywhere. Inside a function, you create a local variable x. Normally, x would just live on that function's stack frame. But look what we're doing. We're returning a pointer to x, its memory address. The compiler's escape analysis sees this and flags a problem. As soon as this function returns, its whole stack frame is going to be wiped out. So if x were on the stack, that pointer we returned would now be a dangling pointer, pointing to garbage. To prevent that disaster, the compiler decides that x has to escape to the heap. It rewrites the code to allocate x on the shared heap from the start. That way, the pointer that gets returned is valid, and the memory will stick around to be managed by the garbage collector.
So let's bring it all together. Here is the final mental model you should walk away with. 1. Normal function calls just add frames to the current stack. 2. The Go keyword is the only way to create a new goroutine and a new stack. 3. The heap is for sharing data or for data that needs to outlive its function. 4. Stacks are always private to a single goroutine. 5. Stack memory is requested directly from the OS. It does not come from the heap. And 6. These stacks are dynamic. They start at a tiny 2 KB and grow automatically as needed. If you can keep these 6 rules in your head when you look at Go code, you'll have a really deep and accurate intuition for how your program is managing memory.
And we'll end on a question for you to think about. Understanding all this machinery isn't just for fun, it has real-world consequences. Knowing that every single Go statement has a memory cost, and that every time you share data, it probably means a heap allocation and more pressure on the garbage collector, well, that can directly influence how you design your programs for the best performance. So the question is, how will this deeper knowledge change the way you write your next Go program?